Good morning to T.Y.B.Sc students. In previous lecture, we have seen the generating function of Hermite polynomial, and from that function we have obtained some Hermite polynomials. After that, we have seen Rodrigues formula for Hermite polynomial, and also from that we have obtained some Hermite polynomials. Then, in this lecture, we are going to study the properties of Hermite polynomials. In last lecture, we have seen first property. So, in this lecture, we are going to prove second property. The second property is hn of x equal to twice hn minus 1 of x. So, we take the proof. In order to prove this property, we have to consider the generating function of Hermite polynomial. The generating function is given in the form, that is g of xt equal to e raised to 2xt minus t square, and write the power series summation n from 0 to infinity hn of x e raised to n upon n factorial. Okay, then we take proof. So in the proof, we have to differentiate this equation with respect to x. So I will write this part again. E raised to 2xt minus t square equal to summation n from 0 to infinity hn of x e raised to n upon n factorial. So write differentiating above equation with respect to x. So we can write, to differentiate this differentiation with respect to x, so we get 2t e raised to 2xt minus t square equal to summation n from 0 to infinity hn of x, and differentiation is dash e raised to n upon n factorial. Okay, so in next step we write 2t, then we substitute e raised to 2xt minus t square as power series. So summation n from 0 to infinity hn of x e raised to n upon n factorial equal to summation n from 0 to infinity hn dash x e raised to n upon n factorial. Okay, so the next step, we take this t inside the summation. So write 2 summation n from 0 to infinity hn of x e raised to n plus 1 upon n factorial equal to summation n from 0 to infinity hn dash x e raised to n upon n factorial. Okay, then in next step we have to compare the coefficients of t raised to n on both sides. So we name this equation first, and we are going to compare the coefficients of t raised to n on both sides. Write this equation. 2, we have substitute here. Here is n plus 1, so we substitute n as a n minus 1. Write this hn minus 1 of x e raised to n upon n minus 1, right, equal to summation hn dash of x upon n factorial. Okay, then write this equation as twice n hn minus 1 of x, right here. T raised to n is not here because we are comparing coefficient of t raised to n on both sides. Write only this twice hn minus 1 of x upon n minus 1 equal to hn dash x upon n factorial, right here. That is n minus 1 into n factorial equal to hn dash x upon n factorial. Okay, so this become n factorial, this become n factorial, and our property is hn dash equal to twice n hn minus 1 of x. So we have to write this hn dash x equal to twice n hn minus 1 of x. Therefore hn dash x equal to twice n hn minus 1 of x. So this is the proof of second property. Then we consider next property, that is number 3. So the next property is prove that hn of x equal to minus 1 raised to n hn of minus x. Okay, so we have to prove this property. Then we take proof. To prove this property, first we have to consider the generating function. So write here generating function g of xt equal to e raised to 2ht minus t square equal to power series summation n from 0 to infinity hn of x e raised to n upon n factorial. So make this equation first. Now here we are going to do transformation, that is making transformation such as x equal to minus x dash and t equal to minus t dash. So substituting x equal to minus x dash and t equal to minus t dash in equation first. Right here e raised to 2 minus x dash minus t dash minus t dash square, okay, equal to summation n from 0 to infinity hn of minus x dash minus t dash raised to n upon n factorial. Right? So in next step to write e raised to 2ht minus t square, because minus minus plus and this square t dash square, this is get plus, so negative sign as it is, equal to summation n from 0 to infinity hn of minus x, then minus 1 raised to n t raised to n upon n factorial. So here is a dash, okay, right here is dash, t dash raised to n, here is dash, okay. So in next step we write I have forget to do the dash, okay. So this is equation second. So in next step here we have used x dash minus x dash and minus t dash as the dummy variable. So we replace that by x and t. So we replace here e raised to 2xt minus t square equal to summation n from 0 to infinity hn of minus x, then minus 1 raised to n t raised to n upon n factorial. So in next step we write e raised to 2ht minus t square equal to summation n from 0 to infinity minus 1 raised to n, then hn of minus x t raised to n upon n factorial. Okay, so here we substitute as the power series right here, summation n from 0 to infinity hn of x raised to n upon n factorial equal to, right, summation n from 0 to infinity minus 1 raised to n hn of minus x raised to n upon n factorial. So equation number, right, 3. Now here we compare coefficient of t raised to n upon n factorial on both sides. So comparing coefficient of this and this, so write this hn of x equal to minus 1 raised to n hn of minus x. So this is the proof of property third. So property third. Okay. So then we see fourth property. So next we consider property 4, and property 4 is the orthogonality. Orthogonality. Okay. In previous lecture, when we start the special function, at that time we have seen the Legendre polynomials, and in that Legendre polynomial we have seen the orthogonality property. So Legendre polynomial satisfy the orthogonality property, but in case of Hermite polynomial, this Hermite polynomial does not satisfy the orthogonality property. So in this fourth property, where we can write the Hermite polynomial does not satisfy the orthogonality property. So Hermite polynomials do not satisfy orthogonality property. Okay, so by ending to this property 4, the Hermite polynomials and their properties are here. This is the last property of this Hermite polynomials. Then next we consider the Bessel function of first kind, right? Bessel function of first kind. Okay. Now for the Bessel function of first kind, we consider the generating function. That generating function is given g of xt equal to k raised to x by 2 in bracket t minus 1 upon t equal to write the power series summation n from minus infinity to plus infinity jn of x e raised to n. Now if we consider Bessel function of first kind, and its generating function is given in this format, but this Bessel function of first kind does not have polynomials. So further we have to consider only properties of the Bessel function of first kind. So in next lecture we are going to see or prove the properties of the Bessel function of first kind. So I stop here. Have a good day.